All right, so today we're looking at our first topic for kind of the first half of RC circuits that we're going to be looking at, and that's RC stands for resistors and capacitors in series in a circuit. And we're going to look at what happens when we charge a capacitor through a circuit. So quickly and the objective is objective C.3.D 1 through 4. So let me just put that up on screen for a moment and take a look at what those are. And that would be these ones here. So understand the discharging or charging of a capacitor through a resistor. And today mostly we're going to be looking at charging. We'll do a separate shorter lecture for discharging. It's pretty similar. So we're going to understand what we mean by the time constant of the circuit and how to calculate that. We're going to be able to sketch and identify graphs of charge or voltage or current, and we'll see how the time constant affects the graph. We'll have expressions for the charge and the current, and if we know the charge and the current, the expression for voltage is easy to come up with. And let's see, we'll get to this in the problems behavior of several capacitors and resistors. We won't actually be getting to that one today. But we'll get to that one soon. All right, so we're looking at charging capacitors. All right. So here's a circuit. There's a battery with an EMF. The switch is open at the beginning because as soon as we close the switch, things are going to start to happen. So in this kind of a circuit, we want to have a switch. Capacitance C, and a resistor here with a resistance R. Right, and it doesn't really matter. We'll see if the resistor, which side of the capacitor the resistor is on, right? As long as it's in the circuit there as well. All right, so what's going to happen at first when we close this switch? Any ideas? What's going to happen to the current flowing in the circuit? What's going to happen to the charge on the capacitor?
Charge is going to increase in the capacitor, and then the resistor is probably going to nothing's going to happen to the resistor probably.
Well, you're right that the charge is going to increase on the capacitor. We are going to see that, right? Because this is when this is uncharged and we have a higher potential here than we do here, current's going to begin to flow, right? And we'll have positive charges building up here and negative charges building up here as the current flows from high to low potential. And I wouldn't say that nothing's going to happen to the resistor, but the current in the circuit is going to be affected by the resistor, right? The higher the resistance, the less current's going to flow. So how do you think how might the resistor then, and this is just kind of before we get into the details of it, how would we expect the resistor to affect how long it takes to charge, or how long it takes charge to build up on the capacitor?
It's probably going to slow it down because it's going to resist the flow of current.
Right. So that makes sense. The higher the resistance, the more the currents resist, the lower the current, right? The lower the flow of charge. So a bigger resistance, we're going to expect means it's going to take longer to charge up the capacitor. And we'll see that when we figure out what our time constant is and we get into all that. So we expect a bigger resistor means longer to charge up the capacitor. And maybe an easier question is, how is the capacitance, do you think, going to affect how long it takes to charge up? Is it going to take longer to charge a giant capacitor or a small capacitor?
The bigger the capacitor, the longer it's going to charge because it needs more charge to get into.
Yeah, because a bigger capacitor, right? We know capacitance is just how much capacitance is just the potential divided by the charge, right? It's how much charge you can store at a given wait, is it potential divided by charge or charge divided by potential?
Charge divided by potential.
Charge divided by potential, right? That's right. Yeah, I'm sorry. Charge divided by potential. I had that written down the wrong way for some reason over there. It's how much charge you can store per volt, right? So a bigger capacitance is going to mean you have it's going to take more charge to fill up the capacitor, you know, to whatever our EMF is. So we expect a bigger capacitor is going to take longer to charge, and a bigger resistor is going to take longer to charge. So let's find out what happens when the circuit is closed, right? And we're going to close it at time equals 0. And I hope we can see that the charge is going to be a function of time, right? We started out with no charge, and we're going to end up with you know, a fully charged capacitor. So we're going to see charge as a function of time, and we're also, and what other variable are we going to see as a function of time? What's going to change over time? Or it might help to write down the loop rule first. Let's see what happens. We don't have any, you know, we've used Kirchhoff's rules before to analyze circuits, and that's what we're going to do here. We don't have any junctions in this circuit, right? It's just a simple one single loop.
The voltage, the total voltage is going to be 0, right?
Exactly. Yeah, that's what the loop rule says, that if we add up the voltage going around this circle, we're going to get 0, right? So from loop rule, there's only one loop. Right, if we go around the circuit, we start here. We've got a positive EMF going from here to here, right? Going from the negative to the positive. We increase the potential there by the EMF of the battery. And then I go over here, and I reach the capacitor. What's going to be the potential difference across the capacitor? And we remember that
It's going to be the charge divided by capacitance.
The charge divided by capacitance, right? Because we know capacitance is the charge over the potential, right? So you're right that the potential, then our potential drop across the capacitor is going to be Q over C, right? And we're going from a higher potential to a lower potential, so we got a minus sign there. And I'm going to make sure I put in Q as a function of time. Because when we first close the switch, there's no charge on that capacitor, so there's not going to be any potential drop. But as time goes on and we see the capacitor charging up, that's going to change the potential difference on this, in this part of it. It's going to change the potential difference across the capacitor. So then I go around and I come here and I go and I go from here to here across the resistor. Now, what's my potential drop going to be going past that resistor with resistance R? We should be able to, we should know this because we've done a bunch, we've looked at a few loops with
It's going to be the current times the resistance.
Current times the resistance, right? We know that potential difference is current times resistance, right? That just from the definition of a resistor is the potential difference divided by current, right? The equation mistakenly known as Ohm's law. All right, so that's going to be a drop, right? Because again, we're going from high potential here to low potential here. So we're dropping potential. That's a minus sign. So we've got I, and what we're going to see is the current here is a function of time. So I'm going to write I of t, right? Because as we change the as the charge builds up on the capacitor here, right? We're going to be increasing the potential drop over here, and as a result, decreasing the potential drop over here. And really, we're going to be increasing the charge on the capacitor here. And as we remember that current is really just the derivative of charge, which we'll get to and need to use later. Oops, this is multiplied by R. My bad. So current times R is the potential drop going to the resistor. And all I'm saying is current is going to be a function of time because the amount of charge that passes a given point, the current is just the rate that charge passes a given point, right? And as charge builds up on the capacitor, that's gonna change. So that gets us back to where we started. So we've gone around the loop. So this is going to be equal to 0. All right. So this is our loop rule, and what this really is we'll see shortly, is this is a differential equation that we need to solve for Q. And you probably haven't been exposed to solving differential equations yet, but you will be in college if you're going into physics or math or any kind of technical field. So we're going to solve that differential equation here today in a moment. But first, I want to see what happens at time t equals 0, right? So when there's no, we say that we're starting out uncharged, right? So at time t equals 0, so Q of 0 is just going to be equal to 0, right? That's an initial condition. We're starting with no charge on the capacitor. And we can see then, if we know that the charge at time 0 is 0, we can see from our loop rule equation what the current is going to be at time 0. And what is the current going to be initially?
Zero as well.
Not according to this equation. So 0 before we close the switch, right? But as soon as we close the switch, we're gonna have some charge flowing. Right, we're saying time equals 0 once the switch is closed.
So I'm a little confused on how the current can pass through a capacitor.
Well, it can't pass through it, right? The current's going to be flowing in the circuit, and what's going to happen is that as the current flows, right, positive charges are going to build up on this, and simultaneously negative charges build up on this plate.
So once the charges finish building up, the current is 0.
So yeah, you're right, and that's right. So the current is gonna become 0.
I see.
When the capacitor is fully charged.
But at the beginning, it's just going to move according to that single resistor up there. Down there, sir.
Exactly. So we can quickly see what I of 0 is going to be, right? When Q of 0 is 0, right? So at the beginning, this term doesn't exist, and we just have E minus I of t times R equals 0, right? So that means E equals I of 0 times R. So that means our current at 0 is just the EMF divided by R, right? Just what you'd expect with if there was no capacitor in the circuit at all. Right, and that'll be our maximum current, right? And you're absolutely right that as the capacitor charges up, the current's going to kind of die out. It's going to die away and become 0, or really we'll see it asymptotically approaches 0. All right. So that's worth taking a look before we kind of figure out what the formula is for Q of t and I of t. We can say that when fully charged, the current's going to be 0. And what about Q? Do we have a expression for Q when the capacitor is fully charged? I think we do if we go back to our definition of capacitance.
Wait, you said using the capacitor?
Yeah, what's the charge on the capacitor going to be when it's fully charged? And it's going to be fully charged, we know, when the potential difference across the capacitor is just equal to the EMF of the battery.
So we just multiply the potential difference times the capacitance.
Yeah, so Q, and I'll call it Q max because that's going to be the charge when it's all charged up, equals the EMF of the battery times the capacitance. All right, so let's kind of see how it gets there. All right, we're going to get an expression, a formula for Q of t, and then also for I of t. But I is just the rate of change of Q, so it's the derivative of Q. All right, so we want to remember our definition. Oops, remember what? Remember that current is just the derivative of the charge, the rate of change of the of charge. So we've got a differential equation here. We've got an equation of a function and its derivative is inside the same equation. Right, so I'm going to replace my I of t with dq dt. I'm going to divide everything by r. And if I do that, I get e over r minus q of t over rc. I'm going to add this to the other side then, is going to equal my dq dt.
So will there be two types of current?
Two types of current? What do you mean by that?
Sorry, two values of current in this circuit?
There's going to be. Mhm.
Because there is one side who has a resistor and the other one doesn't.
Oh, well, no, it's all one loop. You still treat it as one loop, even though the charge can't actually get from this plate to that plate. The current's still gonna flow the same, and it has to do that. It has to be the same.
Oh, I see. Because the charges are pulling on each other, and
Yeah.
if there is less charge on one side, it's not going to pull as much on the
Right.
positive charge. So it's always going to have an equal amount.
Right, because we know that whatever Q is, there's going to be plus Q on the top plate and minus Q on the bottom plate, and those two will always have the same magnitude of current.
I see.
Yeah, so the current's always going to be the same at any given time. The current's going to be the same throughout the circuit, right? But as time goes on, the current is going to change, right? So I don't think, and correct me if I'm wrong, but I don't think you do any differential equations in your calc classes, right? Even in DC. Is that a familiar term, differential equation?
Yeah, we do.
You do them?
Yeah.
Okay, great. So then maybe you do know how to solve this, right? So the idea is we want a function for Q that's going to satisfy this equation, right? That when we do, this constant minus our function divided by this constant, we get its derivative. Right, so there's some function Q that's going to fit this equation, and differential equation, depending on what the equation looks like, this can be very difficult or pretty simple to solve, right? And there's a lot of different techniques throughout that you'll use to solve differential equations, and this one turns out to be one of the easier differential equations to solve. It's separable, and we just kind of get dq on one side and dt on the other side, and then we integrate and see what happens. But sometimes you have to go through all kinds of difficult techniques to solve a differential equation, and sometimes you can't even do it at all. Okay, so let's see now. I want to get, let me kind of combine the terms over here. So I want to multiply, I want to make the denominators the same. So I'm going to do a C over C in this term. And the other thing I'm going to do is.
Do you know when Mr. Elvis' class is?
No, sorry.
You know when he's 17?
It should be next door.
Okay.
So the other thing I'm going to do is so I've combined these terms, and I just want to switch it so that wait a minute, EC minus Q over T, or minus Q of T. Oh yeah, so let me write it like this. I'm going to put this side on the other. Am I missing a minus sign somewhere already? Anyway, what I want to have is minus Q minus CE over RC equals dq dt. Is that right, or did I miss a minus sign there somewhere?
It should be good.
One second, let me check something here. I think I missed something. Oh, yeah, right, because that minus sign, if I put the minus sign here in front of everything, then it carries through. So this is right. Sorry about that. Okay, so this is what we've got here. This is just rearranged so that now I can say, okay, I want to multiply both sides by delta t, and I'm going to just divide both sides by this q minus ce, right? So that I'm kind of grouping my terms with the q in it, and the terms with, well, there's no t explicitly, but I want that by itself. So again, this is, I'm separating this this equation here, the dq on one side and dt on the other side. So I'm going to divide, so I'm going to get, if I multiply this side by dt, I'm going to get minus dt over rc. And on this side, I have dq over q minus capacitance times EMF. So I think this is how I want it now. I can be able, now I'll be able to integrate this. All right. So this side's in dt is the integral, t is the variable of integration. So I want to integrate this from 0 to t, my time. And I'm going to integrate from this to 0 to the maximum charge, right? And I'll put to q max. Okay. So let's see. And what do I get? What would I get if I integrated this? This is a simple one to integrate because there's no t anywhere in this. Can anybody tell me what I'm going to get when I integrate the left side here? Well, what's the integral of dt, right? This is a constant, so I can pull out the 1 over RC. Well, if I was integrating x, what's the integral of just dx? The antiderivative, right? What function has a derivative of 1?
X.
Yeah, just x. And in this case, since we're doing t, it's just t, right? So if I integrate this and it, you know, from 0, I'm just going to get 0, and then from t, I'll get the value for time. This side, I'm just going to have minus t over RC. All right, when I do that integral, and I don't want to take too long to worry about doing these integrals. Some of you'll be able to do them probably, some maybe not yet, but that's all right. But then I'm going to integrate this side, right? And this side, I do have a q over here, and it's in the denominator, right? So I'm going to end up with a natural log, because I know if I integrate a function of, you know, dx over x, or in this case dq over q, I'm going to get a natural log, and it should work out in this case, since it's q minus ce. What I should get is the natural log of q minus ce over minus ce. Right, when I integrate, and that's really q max. That should be in there. Q max. No, this is just q. I shouldn't call this q max. This is for any charge q at any charge at any time t. All right. So again, we don't need to go too deep into how we compute this integral and get this. But if you're familiar with integrating functions, you know, dx over x and that kind of thing, you're probably used to seeing that come out to be a natural log, right? Or if you know that the derivative of the natural log is 1 over the function. So this is enough. Now we can finally get our function, our expression for Q, the charge on the capacitor as a function of time. If we exponentiate both sides, right? If we raise both sides to the power of e, if we raise e to the power of both sides, we have e to the minus t over RC over here is going to equal Q minus CE over minus CE. All right, so and then if I want to get Q by itself, right, so I'll multiply both sides by CE or by minus CE. So I get minus capacitance times EMF times e to the minus t over RC equals Q minus capacitance times EMF. And then I just need to add capacitance times EMF to both sides. And that's what I get. And now the very last thing I'm going to do is just factor out the capacitance times the EMF. And I'm going to have that my charge as a function of time is capacitance times EMF times 1 minus e to the minus t over RC. All right, so it's an exponential function, right? And it's going to be it's 1 minus an exponential function. So if we graph this, do we know what this is going to look like? Are you familiar enough with these kinds of functions to know what this is going to look like? I graph charge as a function of time.
I wouldn't say I do.
All right, well, that's okay. So let's see then, if at time 0, right, we have e to the minus 0. What's e to the 0 going to be?
1 over e.
Is that right?
No.
No.
Wait, I'm stupid. Never mind.
Anything to the 0 power.
Oh, just be 1.
Just be 1, right? So at t equals 0, this exponential is 1. So we have 1 minus 1 down here. So it starts out at 0, right? As t gets really big and close to infinity, right? E to the minus infinity is going to be 0. So it's going to, as time goes on, this is going to approach 0, and 1 minus 0 is just 1. So it's going to approach 1 over as time gets bigger. Okay. And since everything's going to be multiplied by CE, that's going to be the value that it approaches. And that makes sense because way up here, we said that the maximum charge is going to be equal to CE. So we're going to have a function that looks kind of like this. It's going to be an increase, and then it's going to asymptotically approach, but never quite, never technically really gets there. Okay. So this is how it charges, right? We start out with no charge, and as time goes on, we asymptotically approach the maximum value of the charge, which is the EMF times the capacitance. All right. The other thing we want to look at is what happens to the current. And once we know the charge, the current's pretty easy to calculate because remember, the current is just the derivative of the charge. So all we have to do is take the derivative of this function. Right, and if we take the derivative of this function, right, we get CE times the derivative of minus e to the minus t over RC. So that's going to be, well, we have CE times, we're going to have a minus 1 over RC factor from up here times e to the minus T over RC. Right, and this is all negative as well. So we have another minus sign out front because this is minus. So the minus signs cancel here, and the C, we have a C's cancel. So what we get for our current as a function of time is just E over R, EMF over R, times e to the minus T over RC. Okay, so this matches up with kind of what we would expect, right? Because at time zero, right, we expected the current just to be the current as if there was no capacitor in the circuit, E over R, EMF over R. And at time zero, e to the minus zero, e to the minus anything is 1. So I of 0 is just that value, E over R. And then what happens as time goes on? What does this function look like? Current as a function of time. You know, it starts at
It starts off like at its highest and then it goes down. So
yeah, it's an exponential decay, right? It starts off at its highest value, right? When this exponential is 1, or the exponential is 1, so the current is E over R. And then as time goes on, right, as time gets bigger, e to the minus time is going to asymptotically approach 0. So the current starts out with the current as if there was no capacitor, and then over time it decays away and it asymptotically approaches 0. So if we wait long enough, it comes close enough to 0 that it looks like there's no more current at all. All right, so the important thing to know here, or the important thing to see, rather, you know, it's not hugely important that you can do these integrals, calculate them out. But the point is, this is a differential equation. So this function for Q of T is this maximum charge times 1 minus e to the minus T over RC or whatever. That's the only function that works if we plug it into this equation, right? And I don't want to go through it, but if we do plug our function for Q that we got in here and our function for current that we got in here, those are the only functions that work, you know, that'll satisfy this loop rule and make it go to 0. Right. So even if you're confused by the process of integrating and figuring out what this function was, you should still be able to see that these are the functions that satisfy our loop rule, and that's how a capacitor is going to charge. All right. So the only other thing to say here has to do with, if we look at the exponential in here, we have a T over R times C. And if you look at the units, right, any exponential, this has to be unitless overall. And if you look at the units, if you look at ohms and farads and combine them correctly, and combine them, an ohm times a farad, we'll see equals a second. So this RC is often known as the time constant, and sometimes it's written as tau. So the time constant RC. Now it's not the time, we can't really talk about the time it takes to charge the capacitor fully, right? Because the capacitor is not really fully charged until time equals infinity, right? And the current doesn't really drop to 0 until time equals infinity, because, you know, it only asymptotically approaches. But RC is a good measure of the time, because that's the time. Well, we define it, or it's defined if you look at it. If you look at what an exponential is, it's the time for the current to decrease to 1 over E of its original value. Right. So it's really about the time it takes the current, and 1 over E it's not really a third, but it's if you think of it as a third, that's a good way to think of it. It's the time it takes the current to reach a third of its original value. So if your max current was, or if your original current was 3 amps, after this time constant, whatever you get, R times C goes by, you should be down to about 1 amp. And then after another RC amount of time goes by, you're down to a third of an amp. And another RC amount of time goes by, you'd be down to a ninth of an amp, and so on. All right, so that's really what the time constant means. Time for the current to decrease to 1 over E of its initial value. Right, so that would be about, I'm just kind of ballparking it, but this would be about here, time equals RC. And you have a similar thing here, right? This is kind of, it would be as the charge increases, it takes a time RC to increase to, I guess it would be 2/3 of its maximum value. So I know that one's a lot, and especially if you haven't seen many differential equations, and I don't think I did a super great job of explaining the integration part of it. But the point is that once we do the integral and we get this formula, this is the only function that satisfies this loop rule equation, right? That has it, and it's a differential equation because it's got the charge and the derivative of the charge, which is the current, in the same equation. So when you solve a differential equation, you're looking for which function is going to fit. And that's how we end up with these exponential values for charge and for current. So questions about this? All right. So if there's no other questions, then we can stop the recording here for today. And next time we'll look, it'll be much shorter. It's kind of a similar thing to look at what happens, what these functions look like when the capacitor discharges. So that'll be next time. Whoops. I'll end the meeting and stop recording.